Hi everyone, in this video we're going to cover the first section of the course, section 1.1, Systems of Linear Equations. We start out with some straightforward definitions. I'll read through them, not entirely, pause the video, skip forward, whatever you feel most comfortable with based on your prior knowledge. We define a linear equation in variables x1 through xn, so that means that, x1, x2, x3. This is in place of, in other courses you may have used x, y, z, a, b, c. We use x's with subscripts in this course. And it's an equation that can be written in this form. That's a linear equation. Those are all subscripts, no superscripts, right? X squared, x cubed. We're not going to see that. Okay, so we have our coefficients, a1 through an. And again, our variables x1 through xn, and b is also a constant there on the right-hand side of the equation. A system of equations is a collection of one or more linear equations involving those same variables. So system can refer to one equation, two equations, three, etc. on up. Couple of more definitions here. We have a solution to a system is the list of values that makes each equation a true statement when those values are substituted in for our variables. And then the set of all possible solutions is called the solution set to our linear system. And two systems are equivalent if they have the exact same solution set. So lots of terms and definitions that we're going to use throughout the semester. We just kind of get thrown at us right at the beginning of section 1.1. Now, a system of equations has three different properties, three different outcomes. It can have either no solution, or exactly one solution, or infinitely many solutions. And what properties the system has, that is something that we will investigate throughout the course, and that will lead us to lots of interesting conclusions. Let's put it that way. Our system can either be consistent or inconsistent. Inconsistent meaning no solution, consistent meaning one or infinitely many solutions. Now, on this slide, we look at how we can encode a linear system into a rectangular array, which is called a matrix. And this notation is something that we will encounter for, the next 15 weeks of this course. Okay, so the coefficient matrix for the system at the top is what we see in our matrix down below. Notice with the matrix we use our square brackets with the lines like that. Okay, a lot of times people will use brackets like that. Please don't do that. That means something different in linear algebra. So make sure that you do square off those brackets with the little notches on the top and bottom. Okay, and then if you take the coefficients from the first equation, 1, -2, and 1, coefficients from the second equation, 0, 2, and -8. We see that down in the second row of our matrix. And then the third equation, -4, 5, and 9. That is called a coefficient matrix. Matrix of coefficients is the less commonly used order of words, but it's a coefficient matrix for that system. So when you see the term coefficient matrix come up in our book, know that we are just referring to the left-hand side, the coefficients of the variables in our system. Now that contrasts with the term augmented matrix. Okay, an augmented matrix, we tack on the constants from the right-hand side of the equation. So if you want to flip back in the video a few seconds, the right-hand side of each of those three equations, 0, 8, and -9. Okay, and what you will often see when you do have the equal sign and everything is you'll often see a dotted line. Our text does not really use that. I occasionally will. I often don't, but that's what that means. That it's signifying that we have an augmented matrix, and what's on the right of the dotted line is the right-hand side of each equation, the constant term. Okay, so there's our augmented matrix definition. Okay, here we come to another definition. This is the size. Sometimes it's referred to as the order of a matrix. Our text uses the word size, but in the past, when I took linear algebra, the word that my book used was the order of a matrix. It tells how many rows and columns it has. So we have an m by n matrix, where m and n are positive integers, and m is the number of rows, n is the number of columns. So down here, if I draw myself a little matrix. 1, 2, 3, 4, 5, 6, 7, and 8. I count my rows first, 2, and then my columns. So it's always row by column. Ingrain that into your soul. That is a 2 by 4 matrix, row by column. Do one more example here. We'll do a really tall matrix. 1, 2, 3, 4, 5. Okay, so how many rows does that have? That has 5 rows by 1 column, a 5 by 1 matrix. Now, the second bullet point here, it says the basic strategy for solving a linear system is to replace one system with an equivalent system that is easier to solve. Okay, and we'll see what that looks like as we go through lots and lots of examples. And our first example is the system that we were presented with previously. We're going to solve the given system of equations and see what the solution set looks like. But what I want to do is kind of side by side. We're going to solve it in an old school way using elimination methods, so not using any matrix algebra, but using algebra that you may have learned in some high school course, maybe just with 2 equations and 2 variables. But we're going to use the things we've seen in the past, and in each step, write down what that looks like with an augmented matrix. So the first thing that I'm going to do is just rewrite my system over on the left here. I have x1 minus 2x2 plus x3 equals 0. 2x2 minus 8x3 equals 0. Negative 4x1 plus 5x2 plus 9x3 equals negative 9. All right, so I want to solve that system, but first let's write our augmented matrix, right? This one we already had in an earlier example. 1, negative 2, 1, 0. Just going across that first equation. 0, 2, negative 8, 0. Negative 4, 5, 9, and negative 9. All right, so what we're going to do now is we're going to take and use some algebra steps. I'm not going to worry about that middle equation. Notice that middle equation only has 2 variables. We're going to take the top and bottom equation and try to eliminate one variable. And the variable I'm going to pick is my x1 variable, because then I will have a 2 by 2 system that's easier to solve. Okay, so I want to take that top equation and multiply it by 4, by positive 4, and that's going to help my x1s to eliminate. All right, so let's see what that looks like. We're going to have 4x1 minus 8x2 plus x3 equals 0. I'll rewrite my middle. 2x2 minus 8x3 equals 0. And then the bottom equation, 4x1 plus 5x2 plus 9x3 equals negative 9. All right, great. So now let's combine the top and bottom equation. And what I'm going to do when I combine them is I'm going to, let me draw a horizontal line here. There we go. When I combine them, I'm going to keep my top equation the same, minus 8x2 plus x3 equals 0. I'm going to keep my middle equation the same, equals 0. Now, I'm just noticing a mistake here. If you caught it earlier, pat yourself in the back. That middle equation is wrong. It should be 2x2 minus 8x3 equals 8. So let's use red. Oops, and it's too small. And correct it right there. Correct it right there. Ooh, I can kind of fudge it right there. And correct it right there. 2x2 minus 8x3 equals 8. Again, if you caught that earlier, good job. Now we all have, hopefully we're all on the same page. Okay, so what I was doing, combining my top and bottom equation there in green. So I'm adding this row and that row together, and my x1s will eliminate. 4x1 minus 4x1 is 0, but I'm not going to write that down. Negative 8x2 add 5x2 is negative 3x2. Positive x3 plus 9x3 is 10x3, and 0 minus 9 is negative 9. Great. Okay, so Pause the video if you need to see how that calculation worked again, or pause it and just like process it more fully. But I'm going to keep going with the example. All right. So what I want to do next is rewrite that as a matrix. Whoops, not like that. Rewrite that in matrix form. So I didn't change the first row. 4, -8, 1, 0. Didn't change the second row. 0, 2, -8, 8. But the bottom row now says 0, -3, 10, and -9. Cool. So we changed that bottom row. We have an extra 0 in our matrix. All right. Now let's do the next step, the algebra over on the left-hand side. And we're going to take those bottom two equations now and eliminate another variable. Okay. So I'm just focusing on, I'm going to highlight them. I'm just focusing on these two equations. I have two equations and two variables, so let's do some elimination. Okay. I'm going to multiply the top row by 3. That's going to give me 6x2. Actually, let me write that down. 6x2 minus 24x3 equals 8 times 3 is 24. And I'm going to multiply the bottom equation by 2. It gives me negative 6x2 and 20x3. And that equals negative 18. Okay, so let's see what happens here. I'm going to drop my first row from earlier. That's not changing. 4x1 minus 8x2 plus x3 equals 0. I'm going to rewrite my middle row, the original middle row, this guy here. 2x2 minus 8x3 equals 8. So yes, I did multiply it by that 3 there, but I could just as easily divide the 3 back out. I want to work with smaller numbers if I can in like my future steps. Okay, but now I have a new third row. That new third row comes from combining those two rows right there. All right, and what are we going to get when we combine them? My x2's cancel out, giving me a 0 there that I'm not going to write down. Negative 24x3, add 20x3 is negative 4x3. 24 minus 18 is 6. Now let's write that in our augmented matrix form. Row 1, 4, -8, 1, 0. Didn't change. Row 2, 0, 2, -8, 8. Didn't change. Row 3, 0, 0, -4, and 6. All right. So we're making progress here. Okay, so what we do now is, well, I have that bottom equation that almost is solved for x3, isn't it? Right? All I need to do is divide everything by -4, and then I get x3 is equal to, let's see, 6 over -4. That's -3/2, or -1.5 x3. Cool. All right, so we already know what one of our variables is. Well, already. This is a kind of long problem, but I'm doing it side by side to really walk you through and show you how this process works. I want to write a new augmented matrix since I know what one of my variables is. 4, -8, 1, 0, 0, 2, -8, 8, 0, 0, 1, -3/2. Cool. All right, so what's my next step? I have one variable. Now I'm going to use that. I'm going to back substitute that into the previous equation so I can solve for my next variable. All right, so let me go. I'm using lots of colors here. Let's take that middle equation, 2x2 minus 8 times -3/2 equals 8. And I want to solve for x2. Let's see, that's 2x2. It's going to be plus 12 equals 8. Subtract 12, you get -4. Divide, and you get x2 as -2. Awesome. All right, so let's write a new augmented matrix. We're making progress here. Row 1 didn't change. 4, -8, 1, 0. Okay, I have a new row 2. All I have is x2 equals -2, and what that looks like, translated into the middle row, is no x1s, 1 x2, no x3s, equals negative 2. And then the bottom row, 0, 0, 1, negative 3 halves. Okay, and so what we see there is that when you have a variable, when you've solved for a variable, we have zeros everywhere except for where that variable is. You have a coefficient of 1. All right, last equation, top equation, we're going to back substitute, and that is, oops, went a little bit too high. There we go, now I can see it. So that top equation is 4x1 minus 8 times negative 2 plus negative 3 halves equals 0. All right, and let's see what we get when we solve for x1. Let's see, we're going to, let's see, 4x1 plus 16 equals positive 3 halves. Subtract 16. And I think that we should get, let's see, 16 is 32 over 2. So I want to say negative 29 over 2, negative 29 halves. That sounds about right. And then when you divide that guy by 4, x1 equals negative 29 over 8. So we got a couple of ugly, well, one ugly fraction in this one. 3 halves isn't that bad of a fraction. Hopefully you were able to see how these side-by-side comparisons worked out, right? The process on the left, lots of writing, horribly inefficient. And what we're going to be able to do, well, let me first write my final product here. There's my middle row, 0, 0, 1, negative 3 halves. There's my bottom row. Top row comes from this equation, x1, so there's a coefficient of 1 in front of that. No x2s and no x3s. Negative 29 over 8. Okay? As I was saying before, the process on the left is very inefficient, and what we're going to be able to do in these first couple of weeks of the course is learn and understand how to transform each of these matrices into the subsequent steps below them. So not writing it out algebraically, and some of you might need to do that side by side initially, which is perfectly okay to start the learning process, but ultimately you want to be working just within our matrices. Okay, some more notes on this next slide. We're going to define 3 different elementary row operations. Okay, so these are the basic operations that we will use throughout the next 15 weeks of this course. We have a replacement operation. You replace one row by the sum of itself and the multiple of another row. And this is the one that's most common. They're a little bit complicated to work through the calculations, okay? But this is one that you will want to get the hang of as we start going. And I'll write down what it looks like. A replacement operation looks like this. We're going to say, all right, I'm going to take 2 times row 1. That's the notation. I want to add row 3, and I want to store the result. That's an arrow there. I want to store the result in row 3. So we're replacing one row, that's the R3, by the sum of itself, R3, and a multiple of another row. Okay, so that's a row replacement operation. Next is interchange. This is one just to make your matrix look the right way. To interchange 2 rows, all we go is, all right, I want to take row 1 and flip-flop it with row 4. Okay, double-headed arrow there. I'm just switching these 2 rows. I'm letting my professor know what I'm doing from this step to the next, or doing it so I remember when I look back at my notes. And then scaling a row, multiply all entries in a row by a non-zero constant. What that looks like is I want to take 1/3 of row 3 and put it right back where it belongs and put it in row 3. So scaling always ends in the same place that it starts. Switching, obviously that's how it works. And with our replacement operations, you always have to say where you're storing the result. All right, and then 2 matrices are called row equivalent if there is a sequence of operations that transforms one matrix into the other. So on the previous slide, all of those steps of matrices, those were row equivalent to each other. One cool thing to note is that our row operations are reversible. So once you have a matrix solved, once you've solved your system, you can actually figure out and go through the operations in the opposite order to undo all of your hard work. But that's just a feature of these matrices. If I have 2 linear systems that are row equivalent, They produce the same solution set. That's good to note. Two fundamental questions. If it's consistent, does one solution exist? And if a solution exists, is it the only one? Is that solution unique? These are fundamental questions that we will address throughout the semester. All right, and to close out the section, we're going to look at one last example, and we're going to determine if this following system is consistent. Hint, hint, it's not, but we'll see what happens to conclude that it is not consistent. And you'll first get an introduction to the row operations, the way that we write them. You don't need to know what the steps are yet, just kind of follow my lead in this section, and later on, I will go through the like, how do I know what to do next kind of questions. But for now, just follow my lead, see if you can follow along with each of these steps. Okay, our first step is to take that system and write it as an augmented matrix. So row 1 looks like this: 0, 1, -4, 8. If you're not sure why I wrote those numbers down, pause the video, see where each one came from. Row 2, 2, -3, 2, 1. In row 3, 5, -8, 7, 1. All right, there we go. So we've got our augmented matrix. Now let's go through some row operations. All right, and the first one I want to do is a pretty simple one. I want to take row 1 and row 2, flip-flop them. 2, -3, 2, 1. 0, 1, -4, 8. 5, -8, 7, 1. So I didn't really accomplish much there, but I've set myself up to go through the rest of the problem, and this is the ideal order of things that you're going to want to do. Again, you don't know why yet, but just like I said, you're following my lead. And what you can also do is once I write the row operation for the next step, see if you can follow through with it. See if you can figure it out by pausing the video and then play and see if you got the same answers as me. All right, so let's write down that operation. Now, I hope I don't scare anyone off with this operation, but here's what it looks like. We're going to take oops, where's my pen? There it is. We're going to take -5 halves, ooh, that's a nice fraction, times row 1, add row 3, store the result in row 3. Now, if you want to think about why I'm picking 5 halves, pause the video for a minute, see if you can figure that out. Otherwise, you'll learn in the future how all of these operations, why we decide on them. Okay, so -5 halves times row 1, add row 3, store the result in row 3. Here's one where you're going to want to rely on your calculator if your fraction skills are not, what you might want them to be. But let's go through this operation. And, oops, that's not big enough. There we go. I'm going to rewrite row 1. I like to write the stuff that's not changing first. I'm going to rewrite row 2, 0, 1, -4, 8. And now let's work our way through and figure out what happens on row 3. So let's use my highlighter with each of these. There we go. So here's the first two that I'm doing the operation on. -5 halves times 2 is -5. Add the 5 in the bottom, and you get 0. Whoops, that doesn't look right. You get 0. Then, -5 halves times -3, add -8. Ooh, check that one in your calculator. But if you do, you should get -1/2. All right, keep going through this one. -5 halves times 2 is -5 again. Add 7 is 2. There we go, 2. -5 halves times 2 is -5. Add 7 is 2. Yes, correct. Good. All right, and then the last one, -5 halves times 1 is -5 halves. Add that one is -3 halves, -3/2. Okay, so there's our first operation. We are making progress in this matrix here. All right, now with my next operation, what you can do if you want is pause the video, take a look at rows 2 and 3, see if you notice anything funky happening there. But, maybe you don't. That's okay, too. My next operation that I'm going to do is I want to take and I'm going to double row 3, add row 2, store the result in row 3. Double row 3, add row 2, store the result in row 3. All right, and let's see what happens. 2 minus 3, 2, 1. 0, 1, minus 4, 8. 0, right? You double this 0 and you add 0, right? That's okay. You double negative 1/2, you get negative 1. Add 1, you get 0. All right. You double 2, you get 4. Minus 4, oh, hey, we got another 0. Interesting. Let's see what happens with the last entry. You double negative 3/2, negative 3. Add 8, and you get 5. Okay, so what happened? Take a look at that bottom row. Again, pause the video if you want before I give away all of the secrets. It's not a secret. But that bottom row says no x1, no x2, no x3 equals 5. That bottom row says, that bottom row says 0 equals 5, to which I say no, I'm pretty sure that those are two different numbers. 0 and 5 are not equal to each other. I have no more variables left on the left-hand side. 0 equals 5, that is false. That is an inconsistent statement. This is an inconsistent system, and it has no solution. Cool. All right, so that is the end of the first section. Thank you for listening. I'm glad that you made it through this one. Hopefully these fractions didn't scare you off too much. We'll encounter them here and there. If you have questions on it, please let me know. Send me an email. Join me in an office hour. I am happy to help you understand something if it wasn't clear. Feel free to watch the video again. Maybe speed it up to double speed. Whatever works for you. Thank you for listening.